So I know I scared you because I mentioned differential equations, but again, we're going to do only very simple differential equations. If you're going to want to learn a little more about differential equations, I suggest you take Etino 3X on edX, fantastic course on differential equations. What we need to know for this course is very little. So our problem is that now with viscoelastic material, we have quantities which are a function of time. We can have strain, stress, elongation. All these things can be also a function of time. And we're going to have relationships that connect the quantity, their derivatives, and in a functional form that is called a differential equation. So what are differential equations? If you have a function y of time, so if you have a function of time, in general it can be a function of anything, but now we're thinking of time because that's the application we're interested in. So say you have something that changes with time, population of ducks in a pond, your money in the bank account, and more commonly this is thought of like position as a function of time. So if I have something that's a function of time, then I can consider also not just how the function changes with time, but I can consider also how the function derivative changes with time. And that's the first derivative of the function, y dot of time. And I can consider how the derivative of the function changes with time. So if I do dy dot of time d time, I'm going to have the second derivative, y double dot of time. So if y is position, this will be your velocity, this will be your acceleration. And then what we have sometimes, in order to figure out what is the particular function or form of y of t, we have conditions in a form that involves the function and its derivative. So for instance, you can have something like a of t log of y double dot of t plus b of t y dot of t plus, and say that y dot of t squared plus c of t y of t equal to some function that you know, whatever function you have on the right-hand side of this equation, right-hand side function of t. So in general, something like this is called a differential equation. And the solution of this can be quite complicated. But we do not need to deal with complicated things. We need to deal with linear first-order differential equation with constant positive coefficients and constant right-hand side. So what does that mean? It means that if I look at this equation here, I say first order. So first order means only y dot and y can be in the equation. So nothing with y double dot or even more can be d cube, dt cube. So none of that, so we can get rid entirely of this term over here. And we want linear. So linear means that the function and its derivative are only in the equation in a linear term like that. So it cannot be squared like that, so the square goes. And then we have constant and positive coefficients. So positive coefficient, so constant coefficient means these things here cannot be a function of time, like that. And also a constant right-hand side, so we can call this guy, instead of right-hand side, we can call it, B, C, D, a constant. So I should cancel out the right-hand side. I should cancel out the fact that it's a function of time. So this can be there, but it's a constant. And so our function now is B y dot plus C y equal to D, another constant. So normally when you write it, it's a good idea to divide by the coefficient of y of t. So even if I tell you b y dot plus c y equal to d, write it in a form in which you divide the term, you divide the equation by the coefficient of the function. And so you rewrite it as something, say a, say c, y dot plus y equal to a constant. Let's call this constant k. And normally, if you look at units, because this is the unit of y divided by time, and this is the unit of y, this constant is going to have the units of time. So normally, this constant here that multiplies y dot is written as tau. So this is so with tau positive. So written like this is a linear first order differential equation with constant positive coefficient and constant right hand side. So written like that, this is in canonical form. So the coefficient of y is 1. And now we need to learn how to solve these equations. So in order to learn how to solve this equation, we're going to take even a further simplification of the equation we're looking at, and we're going to look at this equation in the special case in which k is 0. So now the first thing we're going to do, we're going to learn how to solve this equation for k equals 0. And this is called a homogeneous equation. So equation in which right-hand side is 0, called homogeneous differential equation. So this equation here with k equals 0 is simply tau y dot plus y equal to 0. As simple as it gets. So what does that mean, really? Like, what physically does it mean, this equation? It means that y of time must be such that when I take the derivative, so let me rewrite this as dy dt, and let me bring y on the other side. So that means that dy dt is equal to minus y over tau. So this is dy dt as a function of time is equal to y as a function of time divided by tau. So if I look at any particular time, if I know the value of the function, I divide it by tau, change sign, that must be the derivative of the function. So it means that I'm trying to find the function. I'm trying to find the function y of t such that this is true. So if that is true, what does that mean in terms of what does the function look like? So if I plot out what this means, so if this is my time axis and this is my y of time axis, say that I start at time equals 0, the value of the function as the value y0. Then this equation here tells me you can get the derivative of the function by taking the value of the function. So at time equals 0, that would be y0, divided by tau, and change the sign. So the function is positive, so I'm going to have a negative dy dt. So the derivative of the function as a function of time like this is negative. And the slope is proportional to the value of the function. And so the function means the function is decreasing as a function of time if it starts at y0. And now, because the function has decreased, if I am at a bigger time and the value of the function is smaller, that means also the derivative is smaller. See, because the derivative goes with the function. So the function now here is a smaller derivative, and so on, smaller, 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 smaller. When I go towards time that goes to infinity, what happens to the function? As the time goes to infinity, the derivative is always proportional to the function, but it gets smaller and smaller and smaller. So eventually, y will go to 0 as time goes to infinity. We good? Excellent. So if I now started, I started with y positive. Say that at time equals 0, my y is negative. So this is another function, that has another condition in which the function now has a value y0 that is negative. Well, if the y0 is negative, then I have minus minus over tau. So I have positive derivative. And again, the derivative, the magnitude is going to be big if the magnitude of the function is big, and the magnitude is going to be smaller as the function becomes smaller. So how fast does the function go to 0? Well, it depends on tau. If you have a big tau, so this is the value of the function divided by a big number, you're going to go to the, so if you have tau big, you're going to go to 0 slowly. If you have tau small, you're going to go to 0 fast. So your tau, if it is big, you go to 0 fast. And if it is small, you go to 0 slow. No, the opposite. What am I saying? Upside down. If the tau is big, I go to 0 slow, right? Tau big, I go to 0 slowly. If tau is big, it takes me a long time to go to 0. If tau is small, I go to 0 fast. It takes me little time to go to 0. So you already see that this time has to do with how much time it takes to go to 0. If it's big, it takes a big time to go to 0. If it's small, it takes a small time to go to 0. Okay, so let's see now how this connects to actually the solution, because so far we didn't solve the differential equation. I just looked at it and figured out, based on what the differential equation is, what the function must do. But we can solve it. So how do we solve it? We say, okay, so I start from here, and I bring y underneath, and I bring dt on top. So I rewrite that equation there as dy over y equal to minus dt over tau. Right? I just rearrange things. This goes down, this goes up. And so now this is a relationship between the two differentials. And what I can do, I can integrate the left and right hand side. So if I integrate the left and right hand side, I get that the log, so if I integrate dy over y, that's log of y, and integrate dt is simply t. So I get that the log of y is equal to minus t over tau. As simple as that. But now, because I did two integrals, this is true except for a constant of integration. So I have to write plus constant. All right, so I like this, but I don't like the log in it. So I'm going to exponentiate left and right. So I'm going to do e to the log of y, and e to the log of y is simply y. And then I have the e of the right-hand side. So I have e to the log of y. E to the log is just y. Y equal to e to the minus t over tau plus constant. And now you know that if I have e to the a plus b, I can write it as e to the a times e to the b. You know that. And so instead of writing e to the minus t over tau plus constant, I can write it as e to the minus t over time times e to the constant. And e to the constant is just a constant, so I can write simply as that y is equal to c e to the minus t over tau. So if I write it like that, I see now that these functions here that I had make sense with that, because that's a negative exponential. So this is something that for t equals 0 has a value of c, and then as t becomes bigger, this becomes e to the minus infinity, goes to 0. So we see that this thing is a shape of an exponential, which is what we expected. Okay, at least what I expected. I don't know about you guys, but I expected totally an exponential. So now, what is this c? This c comes from the constant of integration. Essentially, any function which is in this form will satisfy this differential equation here. But most of the time we deal with mechanics, it's not like we can choose any function we want. We have other conditions. So what is the condition that determines the exact solution of the differential equation? Not what family of equation fits this equation, but what is the exact solution that we want? We need something else. So in order to find the solution to this equation, we need to know what are called initial conditions. So initial conditions have to do with what is the value of the function at time equals 0. In general, to determine what the constant is here, I can know the value of the function at any time, and then that will give me the c. But in general, for this class, we're going to deal with conditions in which we know what happens at time equals 0, and from that, we're going to build up to figure out what happens at every other time. So initial conditions, typically, we would know that y at time equals 0 is equal to y0. So if we know that y must be equal to y0 at time equals 0, I can write y of 0 equal to e to the 0, which is 1. So it's c times 1, and this must be equal to y0. So we see that simply c must be equal to y0. So the final solution to my differential equation is that y of t is equal to y0 e to the minus t over tau. And this thing here, once and for all, is the solution to this differential equation here with initial condition that the y at t equals 0 is equal to y0. But and this is it. It's going to look like that. It's going to start at y0. It's going to go to 0 exponentially. And tau is going to decide how fast or how slow it goes to infinity. So let's see actually what tau means now that we know that this is an exponential. We see that for t equal tau, so if I say y of t equal tau, what do I get? For t equal tau, I get y0 e to the minus tau over tau, that's e to the minus 1. So I get y0 times e to the minus 1. So y of tau is equal to y0 over e. So e is just a number, 2.7 whatever. So this tells me that at time equal tau, if I go on this axis and I look at when the function goes approximately to a value which is a little less than half of the initial value. So I look over here, and on this axis, say that I'm looking at this function here, the pink one, this function here, okay, of all these choices. So I'm looking at that function there, and for that function here, I find that the function has gone to y0 over e at this spot here. So at the spot where the function goes to y0 over here, this is my tau. Okay, so now you see why tau is called a characteristic time. It's called a characteristic time because it tells you how much time it takes more or less to get a substantial change in the value of the function, right? So if tau was a week, it will take a week to go from the initial value to the value divided by e, which is less than half of the value of the function. So again, big tau, it means that it takes a long time to get to this y over e. Small tau, it means that you get, so if some function like that would have tau here, which is smaller than that. So smaller tau means the function changes fast. Big tau means the function changes slowly. For this function here, that's your solution with this initial condition. And now we have to go back to figure out then what is the solution if your right-hand side is not 0, but is a constant k. Okay, so let me clean this up, and then we're going to do this part, and then we're all set. Okay, give me a sec.